So now we are in chapter 2, which is complex functions. You are already familiar with real functions. How do you define a real function? From a set A to a set B. F is a function from A to B if it assigns to each value x in a unique value y in B. That we denote by fx, value of f at x. So this definition you are already familiar of a real function. In complex, A could be any set of complex numbers. B is also set of complex numbers. F is a function from A to B if it assigns to each value z in a unique value w in B. We denote w by fz. So what is the difference? In place of a real variable, here we have complex variable z. Now see this example. W equal to z square. This is a function of variable z, which is a complex variable. Let us change it in terms of xy. So z is x plus iota y whole square is equal to x square minus y square plus iota times 2xy. This is real part of this complex function. It is a function of xy, and iota times 2xy, this is imaginary part. So we can write a function into two parts, real part and imaginary part, by changing it in terms of xy. Alright. Next point. X square plus y square equal to a square. This represents a real function. How? Y equal to plus minus a square minus x square. This is a real double valued function. In the case of complex, also there are multiple valued functions. See this example. W equal to z power 1 over 2. What are its branches? Plus minus square root of r e power iota theta over 2. I've changed it to complex. You know z is r e power iota theta. Theta varies from varies in the interval minus pi to pi. But you know this is not defined for z equal to 0. So you can separate out two branches from this double valued function f1z square root r e power iota theta over 2 when z is non-zero, and for z equal to 0 you can define separately 0. So this is one branch of this double valued function. Likewise, you can take another branch f to z equal to minus root e power iota theta by 2 when z non-zero, and 0 when z equal to 0. So point is that as you see multiple valued function in real case, in complex also you have multiple valued functions. Okay. Now, how complex functions differ from real functions in geometry. This is most interesting part. So whatever functions I define, I will discuss the geometry. Geometrical part is very interesting. In real, if you have y equal to fx, how do you see the geometry? You show the domain on x-axis and range on y-axis. After that, you plot the points xy. Means you see the graph of the function in xy plane. But in complex, life is not simple. Region, because w itself carries two real variables. W itself carries two real variables. Z also carries two real variables. This is domain of the function, this one. Domain variable is Z. It carries two real variables. Image also carries two real variables u and v. Means you have four real variables in the complex function. So okay, xy you can show in the xy plane, but where to show u and v? You need a four-dimensional space. That is not practically possible. So how to visualize the geometry of complex functions? Show domain in one plane, the xy plane, means all z. In xy plane you can show easily. And the image of the function can be shown in another plane, uv plane, or you can call it w plane, where you show all w's or images, u plus iota v or u comma v. This is w. So this is how you see the correspondence between domain and range in complex case. You cannot show the two together at one place, but you can show domain in xy plane and range in w plane. Okay. So domain points are in xy plane and range points of the complex function are in uv plane. So we see how the domain transforms to the range under a complex function. We call it complex mapping or transformation. Means how one region given here maps into the complex plane. So you'll see various examples and understand it. In the previous lecture, you learned that complex numbers extend the system of real numbers. So while defining various complex functions, we will use this point that in analogy to real functions, all complex functions are defined. Okay, so let us begin with elementary functions. First, polynomials. You are familiar with polynomials in real numbers. How you define nth degree polynomial in real case, fx equal to a0 plus a1x plus a2x square and so on up to anx power n. In complex case, in analogy to this, you can define a0 plus a1z plus a2z square plus and so on anz power n. What is the difference in real and complex? Now these constants can be complex numbers and z is of course complex variable x plus iota y. So we have defined polynomials in the same way as we do in reals. Okay. Now let us see special cases of it to understand the geometry. First, I'm writing w equal to c times z. If I take a0 0, a2 0, an 0, a1 equal to c, a complex number, z as it is. So it is a special case. You can say linear polynomial. C is a complex number here. Okay. So what do we call this mapping? First of all, we call it rotation and magnification, or contraction also, or contraction. Let us see why. Let us choose C equal to R0 e power iota theta 0. In polar I am writing to understand this rotation and magnification. Z is R e power iota theta. So what do we get as a result? R0 e power iota theta plus theta 0, right? Now in the domain you have Z, R e power iota theta, and range is this, or you can say W. This is R0 e power iota theta plus theta 0. See what changes are taking place under this mapping. R has gone to RR0 and theta has gone to theta plus theta 0. Means if you have a point in xy plane R theta here, what happens to this point in UV plane? R has gone to RR0 means the distance is either magnified or contracted depending on R0. R0 is less than 1, then contraction happens, and R0 greater than 1, then magnification. Okay, distance contracts or increases. All right. And theta has gone to theta plus theta 0 means, let's say it's the case of magnification, then R is larger, means it is RR0, and theta has gone to theta plus theta 0. Earlier it is theta 0, no, theta, it is theta. Now what is it here? Theta plus theta 0. So you see two changes are taking place. One is it is magnified, another it is rotated. That's why this mapping is called magnification, rotation and magnification mapping. Okay, contraction in case R0 is less than 1. So if you have, say, some rectangular area in XY plane, okay, and say your mapping is 1 plus iota z. So under this mapping, what happens to this rectangular area? Can you understand this from this? What happens to this on this mapping? Image of this rectangular region is magnified. Magnified, what is C here? 1 plus iota. So in polar form, it is root 2 e power iota pi by 4. It means this rectangular region is magnified by a factor root 2, and it is rotated also. Each point is rotated by an angle pi by 4. So the whole rectangle is rotated by an angle pi by 4 and magnified by a factor root 2. That's the image of this rectangle in UV plane under this mapping. Okay, so rotation has taken place and the rectangle is magnified also. So this is rotation and magnification or contraction mapping. See the second case. W equal to C plus Z. This is also a special case of this one, right? A0 I have taken C, A1 1, and all other constants 0. So what we call this mapping? Translation. Try to understand why is it translation. Here Z goes to C plus Z. So if it is U plus iota V, let's say C is x0 plus, let's take a simple one, A plus iota B, Z is x plus iota Y, so you have finally x plus A, iota Y plus B. So x is going to x plus A, y is going to y plus B. Or you can say u is x plus A. These are your equations of transformation. U is x plus A, y is v is y plus b. Now try to understand what happens to the point xy. Xy is the point in xy plane, say here, and x plus A, y plus A, that point is in UV plane. U is x plus A. So x is translated to x plus A, means in x direction, this is x direction. Say here is your xy originally, so it has gone to x plus A, point is here, and finally y has gone to y plus b, so finally your point is here, x plus A comma y plus b. The thing is that this point is translated to a distance x plus A, or you can say shifted by A in x direction and B in y direction. Okay, y direction in the sense v, along v. So the point is translated distance A in x direction and distance B in y direction. So say you have a rectangle here and the mapping is 1 plus 2 iota plus z. So under this mapping, what happens to this rectangle? This is an xy plane. In UV plane, this rectangle is shifted to 1 unit distance along x direction, one unit distance along x direction, and 2 units distance along y direction. So in a way, this triangle is translated from this position to this position, means 2 units along y direction and 1 unit along x direction. So that's why this mapping is translation. Okay, there is no effect on the size remains same, only shifting happens, or you can say translation happens. That's why this mapping is translation. So you understand these two special cases. Now see the third case, w equal to z square. This is also an interesting mapping. Let's see what are equations of transformation here. If I change it in terms of xy, then the real part is x square minus y square, imaginary part is 2xy. So u is x square minus y square, v is 2xy. Okay. So we can see the correspondence of some standard things under this mapping. This is xy plane, this is uv plane. So when u is constant, it is a straight line parallel to v-axis, u constant. I'm taking u equal to a, say. So what is the image of this line, or where this line corresponds? What is the pre-image of this line under this mapping? It is x square minus y square equal to a. U equal to a corresponds to x square minus y square equal to a. What is it geometrically? It is hyperbola. It goes like this. Yes. Likewise, if I choose v equal to constant, it is a straight line parallel to u-axis. Say v equal to b. So v equal to b, what is it geometrically? It is hyperbola again, but with axis passing through region y equal to x, right? So from this, can you judge if I choose two parallel lines here to v-axis and two parallel lines to u-axis, this common region, what is the pre-image of this rectangular region, this side? Hmm? Make another hyperbola here also, and another hyperbola here. Now can you imagine this region corresponds to which region in xy plane? This is the common region. So these regions correspond to this rectangular region. So under complex mapping, you can see the pre-images or images of standard curves or standard regions, okay, which are mathematically convenient to understand. In general, you cannot plot this mapping. All right. Let's see this mapping in polar form. W is rho e power iota phi. Let us choose this polar form of W. And Z is r e power iota theta, so it becomes r square e power iota 2 theta. So rho is r square and phi is 2 theta. Let's interpret geometrically these things. R equal to constant. What is r equal to constant in xy plane? Say I choose r equal to 2. You know it's a circle centered at origin of radius 2. So r equal to 2, what is the image under this mapping? R equal to 2 corresponds to rho equal to 4. Rho equal to 4 in UV plane. So image of the circle is a circle again, but radius is squared. This is rho equal to 4. From this you can see this. It means under this mapping, a circle is mapped into a circle with radius squared. Understand the meaning of this also, try to interpret it geometrically. If theta goes from 0 to pi by 2, say, phi goes from 0 to 2 pi, correct? But what is 0 to pi by 2 in xy plane? What is 0 to pi by 2 in xy plane? Theta 0 to pi by 2. No, I was taking 0 to pi, not pi by 2. Yes, 0 to pi. It is the xy plane above x-axis, this part. Half plane above x-axis is represented by 0 to pi. You are familiar with polar system, right? This is the geometrical region represented by 0 to pi. In xy plane, what is it? In UV plane, it is the whole complex plane. So thing is that under this mapping, upper half of xy plane is mapped into the whole complex plane in UV plane, right? So you see how interpretations are made from a given mapping. You will see more examples. So complex mappings are not like real mappings. You have to show domain in xy plane and range in UV plane. Next elementary functions are rational functions. You are familiar with real rational functions, functions of the type fx over gx. So in complex functions of the type fz over gz, where gz non-zero of course, fz and gz are polynomials. Such a function is rational. Let's see some specific examples. W equal to 1 over z. This mapping is called inversion and reflection mapping. Why? Let's see it in polar form first. Rho e power iota phi, choose for W, and 1 over z means 1 over r e power iota theta minus e power minus iota. I would taken z equal to r e power iota theta. So see what has happened to r theta. R theta is in xy plane. This distance is r, whole distance is r, and this angle is theta. This whole distance is r, angle is theta. Okay. This is our theta point. In the image, what has happened? Rho is 1 over r and phi is minus theta. See the effect. Just to explain, let us draw 1 over r and minus theta in this plane itself, though you can show separately in UV plane. So image point is 1 over r minus theta. Theta has gone to minus theta, means this point is reflected in x-axis. Say this angle is minus theta. That's why reflection. Okay. But r has gone to 1 over r. If r is greater than 1, then 1 over r is less than 1. So point is here actually. Image of this point is here in the UV plane. Okay. Why it is called inversion? Because if you write product of r and 1 over r, then it is 1. So these 2 points are inverse points with respect to unit circle. Okay. So that's why it's inversion and reflection mapping. The point is reflected and it has gone to inverse point. Okay, inverse points maybe you are familiar. A and B are inverse points with respect to a unit circle. Say its radius is r. If OA into OB is equal to r square, then A and B are known as inverse points with respect to this circle of radius r. So here r into 1 over r is 1. So we can call these inverse points with respect to unit circle. Alright, let's analyze it further in terms of xy. W is u plus iota v and z is x plus iota y. From this, I can write 1 over u plus iota v equal to x plus iota y. So multiply and divide by u minus iota v here, left side, and compare real and imaginary parts. What do you get? U over u square plus v square, and y is minus v over u square plus v square. Okay. Now suppose in xy plane you are given a circle. I'm writing general equation of circle x square plus y square plus 2gx plus 2fy plus c. G, F, C are constants here. Okay, you know the center of this circle, minus g minus f, radius also. You know it. Now, what is the image of this circle under this transformation? How to find the image? Through the equations of transformation. Convert this equation in terms of u and v using these equations. Whatever you get, that is the image. So let's substitute x equal to u over u square plus v square and y equal to minus v over u square plus v square. See what do you get? U square over u square plus v square whole square, v square over u square plus v square whole square. So I have added the two, plus 2zx u, 2z u over x u square plus v square, minus 2f v over u square plus v square plus c equal to 0. One power is cancelled. Then multiply throughout by u square plus v square. What do you get? C times u square plus v square plus 2zu plus 2zu minus 2fv equal to 0. Am I right? C times u square plus v square plus 2zu minus 2fv. C I have written in front, okay? Now see what do you get from this. Check this calculation again if I'm missing something. I think it's okay. The one is missing. We are missing one. This part one I have to write. Okay. Now, what is it in UV plane? Do you understand? If C is non-zero, I can divide throughout by C, and you can clearly see it is a circle again in UV plane. It means under this mapping, a circle is mapped into a circle again, provided this C is non-zero. C non-zero means the circles which are not passing through origin are mapped into circles again in UV plane. What if C is 0? Then you are left with 2zu minus 2fv plus 1 equal to 0. Correct? What is it? It's a straight line in UV plane. It means any circle, if I'm taking C equal to 0 here, then this circle passes through origin. It means the circles which are passing through origin are mapped into straight lines in UV plane. Okay. So this is interesting that how the complex transformation works. Okay. Now let us see another mapping which we call bilinear mapping. Bilinear mapping. W equal to AZ plus B over CZ plus D. Here A, B, C, D are constants with AD minus BC non-zero. Linear over linear. It is a rational function, of course. Why we call it a bilinear mapping, you understand this. Now why this AD minus BC should be non-zero? See, I can write W equal to A over C plus BC minus AD over C into 1 over CZ plus D. If I divide the numerator by denominator, I can write W in this form. Now if AD minus BC is 0, then this whole part is 0, because this factor is available here and you are left with a constant mapping. Okay, so to avoid this constancy, AD minus BC is taken non-zero. So this is bilinear mapping. But through this representation, you can understand how this transformation transforms the domain point into the range point. See, first what happens, Z has gone to CZ. CZ means rotation and magnification or contraction. CZ has further gone to CZ plus D. Translation, this has gone to 1 over CZ plus D. Inversion and reflection, again it is multiplied by this constant, that means rotation and magnification or contraction. Finally A over C is added, then that means translation. So it is a combination of different mappings that we have learned so far. Okay, so the point Z undergoes various transformations in the bilinear transformation. So this is bilinear transformation, very interesting, mapping in complex. Now let's define next complex function, that is exponential function. You are familiar with exponential function in reals. What is it? Y equal to e power x. In complex, we write e power z. But this is merely a notation. Thing is that how to calculate it. In fact, this is notation. Its definition is e power x into e power iota y. This is how we define exponential function. E power x, we know how to calculate it, and e power iota y, you know, is Euler notation. You can write it cos y plus iota sine y. Okay, so this is the definition of exponential function. In complex case, you can see if I put y equal to 0, it is reduced to the real exponential function. Now how is it different from the real case? In real case, e power x is always positive. You know it, whether x 0, negative or positive, e power x, the output is a positive number. But in complex case, see this calculation. Say I want to calculate e power iota y, iota pi. So according to this definition, here x is 0 and y is pi. So it is cos pi plus iota sine pi. That means minus 1. So for complex exponential function, value can be negative. Likewise, you can check e power 2 pi iota is 1. Cos 2 pi plus iota sin 2 pi. It's 1. Okay. From this, we can further calculate this quantity, this expression. It can be written as e power z into e power 2 pi iota. So because e power 2 pi iota is 1, so it is e power z. What does it mean? Exponential function is a periodic function with period 2 pi iota. Even if I make it 4 pi iota, still the result is same. So you understand the period. So see the differences from the real case. Real exponential function is not periodic, you know that. But complex exponential function can take negative values and it is periodic with period 2 pi iota. So make a note of the definition carefully because that you'll be using in the problems. Next is logarithmic function. You are familiar with a real logarithmic function y equal to log x. It could have some base. What is it? Natural log base e. So how we define logarithmic function in complex case? That is the point now. E power w equal to z. If e power w equal to z, then w defines logarithm of z. Okay, but again this is merely notation. We should know how to calculate logarithm of z. This we can do from this itself. W is u plus iota v and z is in polar form r e power iota theta. From this e power u into e power iota v. This is happening because of definition of exponential function. You can separate these. Now e power u equal to r and v equal to theta plus 2k pi. These arguments can differ by multiple of 2 pi. You know that we discussed this point in the previous lecture. Equality of two complex number in polar form. From this, what is u? It's natural log of r and v is again theta plus 2k pi. So finally, what is logarithmic function? It's a very important formula. You should know how to calculate logarithm of a complex number. It's ln r plus iota u plus iota v, right? It's u plus iota v. You have determined u and v. So v is theta plus 2k pi. Because k is an integer here, that means logarithm is a multiple valued function. In particular, if you choose k equal to 0, then it is principal branch and it is denoted by log z. Log z is ln r plus iota theta. Theta as usual varies in the interval minus pi to pi. Got it? So this is the formula to get logarithm of a complex number z. So what to do? First change your complex number in polar form. After that you can directly use this formula. See this example. Say you want to calculate log iota. So how to calculate it? First you need to write iota in polar form. What is iota in polar form? E power iota pi by 2. So what is r here? 1. Theta is pi by 2. So according to this formula ln 1, that is 0, plus iota theta plus, no, theta is what, pi by 2, so you need to put pi by 2 here. So ln1 is 0, you can remove it. So this is the value of log iota. So you understand this technique? For finding logarithm of a complex number, express your complex number in the polar form. After that, use this formula. It is always multiple valued. You can select principal value if required. Further, you can easily show that e power log z is z, but log e power z is not z, something extra also with this, z plus 2k pi iota. Verify these two results yourself following the definitions of exponential function and logarithmic function. I leave these for you. Next is complex exponent. Complex exponent means how do you calculate z power c, complex power complex. By definition, it is e power c log z. This is the way to calculate z power c. You understand why is it so? You can write it log z power c, e power log z power c, z power c. So this definition is natural for z power c. So suppose you want to calculate iota power iota. Follow this definition to calculate iota power iota. E power iota log iota. Log iota just we have calculated. What was that value? Iota times ln1 plus iota times pi by 2 plus 2k pi. What do you get from this? E power minus pi by 2 plus 2k pi. You see, iota power iota is a real number in the end, following this definition. Okay, so this is how you can calculate complex exponent. Now let us define trigonometric functions. Trigonometric functions. You are familiar with real trigonometric functions, sin x, cos x, tan x, etc. And probably you are familiar with this expression also. E power sin x can be written as e power iota x minus e power minus iota x divided by 2 iota using the Euler notations. And cos x is defined as e means can be written as e power iota x plus e power minus iota x divided by 2. Because complex system extends the system of reals, so in analogy to these two, complex trigonometric functions are defined like this: sin z equal to e power iota z minus e power minus iota z divided by 2 iota, and cosine z is e power iota z minus plus e power minus iota z divided by 2. So when you put y equal to 0, these are reduced to these definitions, isn't it? Following these definitions, you can verify the properties of these functions that you do in reals. For example, if you want to show sine 2z equal to 2 sine z cos z, you can show it easily following these definitions. Okay, so various properties of real trigonometric functions can be verified for complex trigonometric functions because definitions are similar to this. So you can see various properties in the lecture notes. Okay, let me tell you some properties which are useful, which are different from reals. Sine iota y can be proved equal to iota sine hyperbolic y. Are you familiar with hyperbolic real functions? Say sine hyperbolic x. E power x minus e power minus x divided by 2, and cos hyperbolic x is e power x plus e power minus x divided by 2. Alright, so sine iota y, following this definition you can show is equal to iota sine hyperbolic y. Just replace z equal to iota y here and you will find that it is equal to iota sine hyperbolic y. Okay, likewise cos iota y, in this definition put z equal to iota y, you will see that it is equal to cos hyperbolic y. Why I have written this? Because I want to express sin z in terms of its real and imaginary parts. I can write it sin x plus iota y, then I can follow a property sin a plus b, that is sin x plus sin x cos iota y plus cos x sin iota y. But what is cos iota y? This is cos hyperbolic y, and sin iota y is iota sin hyperbolic y. So these are real and imaginary parts of sin z function. Okay, these are real and imaginary parts of sin z function. From this you can notice one interesting thing, that sin z is not a bounded function. In real, in real case, sin x mod sin x is less than or equal to 1. Its values lie in the range -1 to 1. But here it is not bounded. Why? Because this z is any complex number. It is lying anywhere in the complex plane. Y could be as large as you want. But as y goes to infinity, this part goes to infinity. Am I right? Cos hyperbolic y, hyperbolic functions tend to infinity here. You can see as x tends to infinity, both these functions tend to infinity. So cos hyperbolic y goes to infinity as y tends to infinity. And in the complex plane, this xy point can be anywhere. So that's why this is not bounded. This is not bounded, it means sin z is not bounded. Okay. You can also show that psi from this, means take its modulus and square it. You will find that it is equal to sine square x plus sine hyperbolic square y. So from here also this is bounded, but sine hyperbolic is not bounded, so it is not bounded function. So you see the difference between real sin x and complex sin z. Okay. Also, uh, you may interpret its geometry for some standard curves. From this is w equal to sine z. What is u? Sin x cos hyperbolic y, and v is cos x sin hyperbolic y. Correct? Okay. From this, u over cos hyperbolic y is sin x, and v over sin hyperbolic y is cos x. So what is the sum of squares of these two? U square over cos hyperbolic y whole square, v square over sin hyperbolic y whole square equal to 1. Sin square x plus cos square x is 1. Likewise, if I separate u over sin x from it and v over cos x from it, square and subtract, I get u square over sin x whole square minus v square over sin cos x whole square equal to 1, because cos hyperbolic square y minus sin hyperbolic square y is 1. Cos hyperbolic square y minus sin hyperbolic square y is 1. If you know hyperbolic functions, it's easy to verify. Okay, what I can interpret from these two? See, in xy plane, what is y equal to constant? Y equal to constant is a line parallel to x-axis. But from this, if y is constant, what is it? U square over some constant, because when y is constant, cos hyperbolic y is constant, plus v square over some constant whole square equal to 1. What is it? It's an ellipse in the UV plane. It's an ellipse. Okay. So if I choose another parallel line, it's another ellipse. Okay. Now, what if x is constant? X is constant. If x is constant, then we get something like u square over c square minus v square over d square, provided these are non-zero, okay, equal to 1. What is it geometrically? X equal to constant in xy plane, you understand. It's a line parallel to y-axis, but here it is hyperbola, like this. If I choose another parallel line to y-axis, x constant, then I get another hyperbola. So what is this region? It is rectangular region here. It corresponds to which region in UV plane? These regions. These are common to the ellipses and hyperbolas. So you see how we interpret w equal to sin z. Y equal to sin x graph, you can easily tell. Okay, it goes like this. Between minus 1 to 1. But w equal to sin z graph is not like this. You have to see the domain region. It will transform some given region into another region. Here I have taken rectangular region. I am able to transform, means I am able to understand the image region here through the equations of transformation. Okay. So once sin z and cos z are defined, you can further define tan z. Tan z, how to define sin z over cos z in analogy to the real trigonometric functions. And accordingly, other properties can be shown. Now, how to define inverse trigonometric functions? Inverse trigonometric functions. Hope you recall that how to define y equal to sine inverse x. If x equal to sine y, then y defines inverse sine of x. Recall this definition. Same way, w equal to sine inverse z if z equal to sine w. If z equal to sine w, then w defines inverse sine of z. Definition is similar to the reals. Remember that this is merely a notation. It doesn't tell you how to calculate. For calculation, you have to go to the definition. So how to do the calculation for inverse sine z? See, sine w by definition can be written as e power iota w minus e power minus iota w divided by 2 iota. You can multiply it throughout by e power iota w, simplify it further, and get this equation. Okay. Now this is quadratic in e power iota w. You can simplify it. So you can get e power iota w by solving this quadratic equation, and then you can write w in terms of logarithmic function. From your calculations, finally you will get this expression. This is sine inverse z. This is the formula, because you already know how to calculate logarithm of a complex number. So using this formula you can get sine inverse z values. Okay, likewise there are formulas for cos inverse z, tan inverse z in terms of logarithmic function. Please see the lecture notes. I have already defined real hyperbolic functions. Sine hyperbolic x, how to define? E power x minus e power minus x divided by 2. In analogy to this, in complex analysis, sine hyperbolic z is defined as e power z minus e power minus z divided by 2. Okay, same way you can define cos hyperbolic z. It is e power z plus e power minus z divided by 2. Accordingly, you can see properties of these complex hyperbolic functions parallel to the properties of real hyperbolic functions because the definitions are similar. Then you can define inverse hyperbolic functions. Again, how you define inverse real hyperbolic functions? Say y equal to sine hyperbolic inverse x. We'll follow the same for complex. How do you define it? If x equal to sine hyperbolic y, if x equal to sine hyperbolic y, then y defines inverse hyperbolic sine of, or inverse sine hyperbolic of x. Okay, that we denote by this symbol. So same way, w equal to sine hyperbolic inverse z means z equal to sine hyperbolic w. It's similar to this. If z equal to sine hyperbolic w, then w defines inverse sine hyperbolic of z. This is the definition. Now, again, you need to calculate its expression in terms of non-functions so that you can get its values. So, sine hyperbolic z, you know how to define it. E power w minus e power minus w divided by 2. Now multiply throughout by e power w, you will get quadratic equation in e power w. From that you can simplify w in terms of logarithmic function. What is that logarithmic function? Log z plus z square plus 1 whole power 1 over 2. Because you already know how to find logarithm of a complex number, so using this formula you can get values of sine hyperbolic inverse z. So you see the definitions of complex functions are similar to the definitions of real functions, but there is a subtle difference between the two when you go to the geometry. Properties mathematically look same, but when you go to the geometry, these are completely different. Okay. So hope you enjoyed the geometry of complex mappings, and with this chapter ends. In the next lecture we will discuss complex differentiation. Thank you.